So in 9b, the domain of f is now restricted to x's greater than or equal to 0. And what that means for our function is that the shape that used to be pretty parabolic is now just going to be half a 1 because it's only defined when x is greater than or equal to 0 on the right half of the graph. This change is going to have some implications for part 1, where we have to find an expression for the inverse function of f. Graphically, we would do this by reflecting our graph over the y equals x line. Essentially, we're taking a graph where a y was a function of x to a graph where x is a function of y. And it's going to be defined at or above the y-axis. To find the inverse function itself, we would switch the values of x and y in the equation to make x a function of y. So it would be x is equal to 1/2 e to the y plus e to the negative y. Having one y per x value, this function passes the vertical line test, and so it's a real function and our answer for part 1. For part 2, they want you to find the volume generated when the region bounded by the curve y equals f of x and the lines x equals 0 and y equals 5 is rotated through an angle of 2 pi radians about the y-axis. What does that mean? So first we're going to graph everything. So here's our restricted domain function, and we're going to put lines where y equals 1, which is the minimum for this function, and where y equals 5, because it was in the question. And then we're going to write the names for each of these. Next, we're going to write a line where x is equal to 0, because it's the area bounded by y equals 5, x equals 0, and f of x that is being rotated about the y-axis. It's being revolved around the axis, it's going all the way around, and we know that because it's 2 pi radians about the y-axis, so it's going to make a shape almost like a cone except filled in all the way. And now we get to calculate its volume. To find the volume of a solid revolution, as they're called, we're going to use the disk method. So if you were looking at this function from the side and you were to chop it, just chop it in half, you would see face on a circle because it's being wrapped by 2 pi around the axis. So this would be an illustration of what that would hypothetically look like. If we were to make another chop, it would form this disk, this cylinder of a shape. And the way disk method works is you sum up all of the volumes of these disks to find the volume of the entire solid. So to find the volume of just one disk, you need to find the value for its radius, right? And the radius for this shape would be the x value at any given point. And we're going to define this radius as x is a function of y instead, because we're rotating about the y-axis, and that's going to be very important later on. The other important number for this disk would be its height. And the height we're going to describe as just a general equation for any disk as the change in y, because, it's moving up and down by a certain value, right? Now that we know all our terms, let's start finding the volume of a single disk. Now, because it's a disk, it's basically the area of this top circle multiplied by the height, and the area is pi r squared. But instead of using r, we're going to write 1/2 e to the y plus e to the negative y. The area of the top of the disk is equal to pi times 1/2 times e to the y plus e to the negative y, everything but pi squared. Now we're going to start solving, so it's 1/4 pi times square square multiply double, e to the 2y plus e to the negative 2y plus 2, because the e to the y is over the e to the y, so it cancels. Expression is equal to area. So now to find the volume of the disk, we're going to multiply our height times the area of the top section. So it's just like a cylinder, The volume is going to be equal to dy times 1/4 pi times, open parentheses, e to the 2y plus e to the negative 2y plus 2. So back to the entire solid. It's not just made of one disk. It's made of all these disks, like a bunch of them. And the idea is, as the solid is nearing its minimum, each of the sizes of the heights is decreasing. So the change in y is essentially approaching 0. I read infinity, but it's 0, I promise. So to find the volume of the entire shape, we're going to sum up the volumes of all of these disks as their dy value is approaching 0. So you're taking the limit and you're finding the sum, and that is what you use when you are integrating. So we're going to integrate from the minimum value of this function, which is at 1, to 5. And it's important that we're integrating by y because we're rotating around the y-axis. And then we are integrating this function for this volume because it's the sum of all of the volumes of these disks. To integrate our function, first we're going to take out the constant value of 1/4 pi and multiply it by the antiderivative of our volume of disk equation. The antiderivative is the function with a big F instead of a little f, that when you take the derivative of it, it gets the original function you were looking at. Essentially, it's the inverse operation of a derivative, antiderivative, hence the name. And for our function, it would be e to the 2y over 2 minus e to the negative 2y over 2 plus 2y. To evaluate, first we'll write our constant, and then we'll multiply it by the difference between the antiderivative at 5 and the antiderivative at 1. So that would be equal to 1/4 pi times, open parentheses, e to the 2 times 5 over 2 minus e to the negative 2 times 5 over 2 plus 2 times 5 minus the antiderivative at 1, and I went ahead and already changed the signs, so it would be e to the 2 over 2 plus e to the negative 2 over 2 minus 2. I used a calculator to solve it, and boom, you get 8,653.21 as the volume.